Over the last 100 years, the field of medical technology has seen huge advancements, from the first EEG in 1924 to the first MRI machine in the 70s, and even the full sequencing of the human genome in 2022. However, one piece that is standard for every operating room around the world has seen very few improvements: the surgical light. Comparing this system from the 1940s and this system from 2024, you can see that other than the adoption of LEDs over halogen lights, the mechanical system has remained largely unchanged. Research has found that lighting systems are readjusted every 7.5 minutes, and 64% of the time cause a distraction, 10% of the time even requiring multiple people to move a stuck system. Our team identified this problem and decided to validate it. We validated this by interviewing over 30 surgeons, veterinarians, and hospital administrators, along with touring 3 operating facilities and collecting over 35 survey responses. We then took the information we gathered and modified our problem statement to best address the potential customers' perceived needs and begin working on our solution.
During the surgery, you might have to move the lights like this, and then most lights in the operating room have a limited range of motion, where once you get to this point, then you've got to go all the way sort of back around the world, as it were, to get your light into the right position. So you end up spending a little bit of time where the lights they will often fight each other if you get yourself crossed up.
Market research showed that the surgical light industry has a global market value of nearly $600 million as of 2019, North America making up $185 million of that. This is projected to have a compound annual growth rate of 4.5% and reach $850 million by 2027. The main competitors in this industry, despite having large R&D funds, have yet to produce an autonomous system.
With this, I'd like to introduce ARCOL, the Autonomous and Remote Controlled Operating Light. This project aims to create a system capable of autonomously reposition itself to provide continuously optimized lighting and alleviate the need for a member of the surgical team to manually reposition the light.
ARCOL is a ceiling-mounted system with 5 degrees of freedom following common industry standards that follow the line of the sight of the surgeon. If an occlusion is detected, it will initiate a search method to find an unobstructed position. A SICK multi-skin LiDAR will be used to avoid collisions. Since we can't mount to the A&M's machine shop ceiling, we constructed a temporary structure to mimic a ceiling mount. This structure has 2 load-bearing lines with 2 stabilizing beams spanning between the power racks available.
Line of sight was chosen as the tracking method based on the results of customer interviews and surveys. For this purpose, a pair of standard Z87 safety glasses was fitted with a laser pointer that can be tracked as the surgeon moves by 2 cameras on the ARCOL system. One overhead and one on the lamp itself.
The arm's mechanical system itself is built out of 80/20 T-slotted aluminum rails and consists of 1 DC central motor to rotate the whole assembly, 2 linear actuators to articulate the arms, and 2 servo motors to control the light head. For feedback control, the central motor and both servos have built-in encoders, while the linear actuators are fitted with external string potentiometers. A Raspberry Pi 4 acts as the master controller.
At a high level, the code follows a few logic branches, the first being determining the operating mode. If the operating mode is in remote control, then it simply follows user input. If it's in the autonomous mode, then it checks to see if the laser is within view of the light head. If the light head can see the laser, then the light head servos simply follow the laser in the line of sight. However, if it cannot be seen by the light head, then it checks if the laser can be seen by the overhead camera. If the overhead camera cannot see the laser, then it means that the doctor has looked away from the surgical area, and so the light should do nothing until the doctor looks back. However, if the overhead camera can see the laser, then it means that there's an obstruction blocking the light head and casting a shadow, and so it should initiate its search procedure. The search procedure involves using inverse kinematics to determine where the light head is in 3-dimensional space, where the doctor is looking in 3-dimensional space, and then drawing a vector between the two. After converting the vector to a different coordinate plane, you can get the light head servos to track the approximate line of sight of the doctor while repositioning. Then the light head will continue to reposition within the safe working zone until the light head is able to see the line of sight again, at which point it will jump back into the first logic branch and the light head servos will track the line of sight.
The Multiscan 100 LiDAR monitors the surgical room by interpreting the spaces through horizontal fields above the work area. The Raspberry Pi analyzes the LiDAR's output to recognize the light system and the objects in the surgical area. This allows the Raspberry Pi to maintain a safety gap between the light head and the tallest object in the surgical room in order to avoid collisions. As shown in the Multiscan terminal, it can be seen that the tallest object in the room is sensed by the two bottom field evaluations. The surgical light is then placed on the top field evaluation in order to maintain a two field zone safety gap.
Let's take a look at some videos of ARCL in action. Here we see the system rapidly moving the light head from a startup position into a downward orientation for an operation with a cardboard simulated surgeon. The light head first makes minor adjustments to align with the desired lighting angle. The system then detects an operating room obstacle, raises the arm assembly into a safe working zone, smoothly rotates the arm into a better position, and lowers the light head again. Another demonstration shows just how quickly the actuators, motors, and servos respond to remote control input. The ARCL system can position the light head anywhere in the operating room in under 8 seconds, optimizing lighting without any collisions, contamination, or consternation. ARCL is cost-effective too. The prototype cost under $8,500, less than 1/10 of the price of a high-end, non-autonomous system. A potential customer had this to say about our solution.
I'd love to see it in a busy operating room, like in a hospital, because they've got a lot of cases, and if you could save, 10 or 15 minutes per case on long surgeries, that's going to accumulate where you're going to be able to do maybe one more surgery per day, or there's going to be some efficiency where you can get more out of your operating room, as well as make it an easier experience for the surgeon, which on behalf of surgeons I'm always interested in.
Our development of the ARCL system would not have been possible without the support of the following parties. Thank you for joining us for this showcase of the future of surgical lighting technology.